In this video, we'll be discussing about FlashAttention, which is basically a fast and memory efficient exact attention implementation, as the name itself says, with some more IO awareness added. So we will be discussing what is IO awareness and how FlashAttention is making use of the GPU memory and etc. and other details. If you see generally the trend, especially after the ChatGPT 3.5, almost on every daily or maybe every 2 days or one or the other new model is getting released. And if you see a common pattern across all these models, one such thing you can observe is the implementation of FlashAttention and it is not going to be a vanilla attention. So we'll discuss about what is FlashAttention, what I mean by vanilla attention, other things. For example, you take one of the model released recently was Falcon 40. I cannot call it as recently because since it is more than 30 days. But if you see, even those people have gone ahead and used FlashAttention, right, and also multi-query. And if you see it, the implementation of FlashAttention has been used, in other libraries as well. For example, Hugging Face and PyTorch, and recently in NVIDIA's Megatron and other libraries as well. So this paper is really interesting. So we'll split it into two parts basically, and the first part has nothing to do with the FlashAttention. We will be going with the basics of hardware and how it's gonna work and other details, because overall FlashAttention is making use of the hardware more than the software part of it. And the second and the later part of the video will deal with on the FlashAttention and the algorithms and other details. So let's get on to the hardware part of it. Just to recap, we'll go over the CPUs, how a CPU works, or maybe how a GPU works, what are the various terminologies in GPUs, and then we will get started with the FlashAttention. So let's straight away get into the hardware details. Let's have a look at how a data flows in a system. First, the data will be in the hard disk, or it's also called HDD. And if you want to process the data, obviously we need that data in the RAM, or it's called main memory too. So depending on the kind of system you have, you may have L3 or L2 cache implemented, which is a fast memory compared to RAM. And also there is something called L1 cache and registers, which is a faster memory and which will be very close to the CPU, and most of the times it will be inside the CPU chip as well. That's why these two are called on-chip memories too, and these are called faster memories too. And these are all with respect to CPUs. And when it comes to deep learning algorithms, we all know that GPU has the capacity to execute those algorithms much faster compared to the CPUs, just because of the parallelism and some other related stuff too. We will look into those details. And second point to be noted down is, as and when you move from hard disk to L1 cache, the fastness in which the data is accessed, it will be fast. For example, the time which takes to get some element from the L1 cache, it will be typically in the nanoseconds compared to the data if you want to get it from a hard disk, which will be terms of milliseconds or depend on the kind of device which you have. So the latency between these is very high. Similarly, when you consider the memory size, usually hard disk will be having the highest size, and then the RAM, and then the least is the L1 cache, the register. Typically these will be in KBs, and L3 or L2 cache, this will be in MBs, and this will be in GBs. Nowadays it's also going to TBs because of LLMs like ChatGPT and GPT-4 and other things. And so this is with respect to data flow. And let's have a look at how a data flows in the GPU part. So when it comes to the GPU, we'll understand certain terminologies in the GPUs, because though the terminologies whatever we used in CPU remain the same when it comes to GPU too, but there are some extra terminologies as well. something like HBM and other related stuff. Let's see how a data goes through the GPU. So when you say data goes through GPU, we will always say that we have like 16 GB GPU or 40 GB GPU or 80 GB GPUs, right? These are all called GPU memories, and just this 40 GB or 80 GB will stick on to 80 GB memory, so for the rest of our discussion, so that it will be easy for the discussion too. And this memory will be called in various terminology. Sometimes it's called DRAM or global memory, it's called VRAM as well, it's video RAM, and GPU RAM. But all are talking about one aspect of the GPU, that is how much of the memory your GPU is having, right? And after the GPU memory, the data goes into L2 cache, just like they were how we have seen in the CPU part as well. That means data goes from hard disk to RAM to L2 cache to L1 to GPU. In GPU as well, we have several memory hierarchy from DRAM to L2 cache, right? And L2 cache, from L2 cache there will be something called streaming multiprocessor, which is, you may think of something like cores in CPUs. For example, if you take the NVIDIA A100 80 GB GPUs, what I mean by A100 80 GB is 80 GB of GPU memory. It has 108 of streaming multiprocessor, right? We will definitely discuss about how a streaming multiprocessor looks like, but you can consider cores in CPU is somewhat equivalent to streaming multiprocessor in GPUs, right? And we'll look at few of the terminologies in the streaming multiprocessor. So we'll see how one streaming multiprocessor looks like it. And a streaming multiprocessor, depending on the kind of architecture, it may have optional tensor cores or CUDA cores, and definitely it would have registers. And sometimes L1 cache is also called as SRAM, and it's also called shared memory, and combine this is called on-chip memory with respect to GPUs. I will repeat it again. So all the GPUs need not have tensor cores as granted, or sometimes CUDA cores are granted. So it is optional to have the tensor cores and CUDA cores, but we would be having L1 cache or the SRAM, which is also called as on-chip memories, right? We'll talk about tensor core. So tensor core is nothing but a special hardware designed for the matrix multiplication. But CUDA cores are not the one which is specialized like the way which you have tensor core, which are general cores, right? And it is something from the NVIDIA. And these are all called on-chip memory because physically these are the memories which are much closer to the overall the streaming processor itself, right? And each of the streaming processors, I was talking about, we have n streaming processors here. In NVIDIA A100 we have 108 processors. Each of these will have threads, and threads are divided into blocks. In this case, threads are divided into one block and two block. It's also called as thread block, or a group of threads. It's also called as warps. Okay, and each of the streaming multiprocessor has something called warp scheduler. I have not written it here. And their warp scheduler, the job of the warp scheduler is to schedule the warps. That means whenever, let's say, you want to multiply n cross n matrices, so the data goes from all the way from hard disk to GPU, and from GPU to, there are so many streaming processors, and depending on the architecture, depending on the other scenarios, a certain thread block will be chosen or multiple thread block will be chosen, depending on, again, on the size of the data set too. and it will be assigned, and the warp scheduler mainly does these jobs. And apart from these, uh, SM, we usually call it as SM, that is nothing but streaming multiprocessor, also has some kind of processing unit. Usually that will be less compared to the core of a CPU. Usually the processing power of a core of a CPU is much higher than the processing power of SM of a GPU, right? And combined processing power of all the streaming multiprocessor would be the processing power of the GPUs. It is just as simple as such, right? For example, whenever we say 1 gigahertz, right, this is the processing power of a GPU. That means it has the capacity to run 10 raised to 9 cycles in 1 second. In one cycle, there could be one operation can be done, or there could be multiple operations can be done, or a single operation can take multiple cycles to run. So it's always m is to n. So whenever we say 1 gigahertz GPU, we say that means it has a capacity to 10 raised to 9 operations per second, right? For example, if you want to get the data from GPU memory to, let's say, one of the SMs, or maybe let's say one of the tensor cores, it might require, depending on again the architecture, 300 to, let's say, 400 cycles. Let's say if you want to get some data from, let's say, L2 cache to L1 cache, maybe we might require lesser than 200 to 300 cycles, right? So that depends on the kind of task, that depends on various other attributes too. So this is with respect to GPU terminologies. Oh yeah, one more thing. So we have, I think I was talking about tensor cores, right? These tensor cores are fast. They are very fast. They are such fast that half of the times they are idle. Yes, I repeat, these tensor cores are so fast, and most of the times they are idle. It was also found that while training GPT-3 models, these tensor cores were idle almost 50% of the times, and that's how fast these tensor cores are. And when you make a comparison of tensor cores with respect to other memories, tensor cores are 200x compared to global memory, or what we call as GPU memory. These are that much fast, literally like 200x. You can like an approximation of 200x. Of course, that depends on the architecture and other related things. And L2 cache is somewhere around like 3x to 5x faster than the GPU memory, right? And this is somewhere around 5x, and this is somewhere around like 200x, right? So, and though it is 200x faster, and we are saying that we are able to use only 50% of it, and FlashAttention is there just to make use of this. For example, if you want to make, let's say, 50% utilization to 100%, what ideally would be the things one needs to do? I think one can do two things. First is, whatever the data we are getting from GPU RAM to L2 cache to SM, maybe we can increase that data. So when we increase that data, maybe we can able to increase the usage of the tensor cores. And second thing is, if we want to increase the data, of course the data should be big enough to fit into L1 shade or SRAM, that is for granted. And second thing is, if you want to get that big enough data which sits on SRAM, we need enough bandwidth from the GPU memory so that we can pass the data from GPU memory to L2 cache to L1 cache or the SRAM of the streaming multiprocessor. So two things needs to be done. One is having a bigger bandwidth and big enough data in the SRAM. So we'll take a couple of steps back. We were discussing about 880 GB RAM. How it is implemented is using a technology called as HBM. That means high bandwidth memory technology. There are various ways in which 80 GB memory can be implemented in the hardware side, and HBM is one such technology. And the technology is implemented in terms of stacks. For example, if you take 80 GB, 80 of one 800 NVIDIA GPU, it is implemented in 6 vertical stacks. Why vertical stacks? If we implement it in that way, we can make use of the bandwidth easily. That means higher bandwidth is more feasible if we implement it that way, right? In 800 literally has 6 stacks, 6 vertically implemented stacks, out of which only 5 stacks has 16 GB memory. Out of 6 stacks in the 880 GB GPU, only 5 stacks have the memory, and each of the 5 stacks has 16 GB memory. That means combining together of all the 5 stacks will end up with having 80 GB, using which we can able to have the high bandwidth memory technology. This is what called hybrid. And why can't use 6th stack, or why are you not using, that is with respect to hardware details and physical constraints and lot of other logical details too. We'll just stick on to this. So long story short, HBM is one such technology to make sure that we are making use of the high bandwidth, which is much required if you want to make more usage of the tensor cores and CUDA cores, right? And this is all with respect to the GPU terminologies. And let's go further. And the last one before we end up, we already discussed about clock speed. That is, I was talking about 1 gigahertz, nothing but 10 raised to 9 and 10 raised to 9 cycles. Some of the, if you want to finish one of the operations, it might require more than one cycle, or certain operations are so lightweight that can be finished in one cycle. It's always m is to n. So there is something called flops. That means floating operations per second. Usually the speeds of these are measured in floating operations per second. Let's say we'll talk about these flops, of course, down the line, right? And so let's have a look at the vanilla attention in short, because I have already made a detailed video on the vanilla attention. I will also keep the link of the attention video which I have made in the description section of this video. But long story short here, the time and space complexity of the vanilla attention is order of n square. I'll summarize what is a vanilla attention, but if you want to detail, go and watch the videos. So if we have a 5112 token length of a input for each query and each token, and we're talking about one head, right? Each token will have a query, and if you want to compute the attention scores for that token, we will be taking the keys of the rest of the tokens, and key will be multiplied with the query, and that will be scaled down, and we will be taking the softmax of this multiplication, and then we will be multiplying with the value vector. Basically, if you observe this, literally we are having order of n square operations. For each of the tokens, we're going to get some value, right? And to get the value, we will follow the order of n square operation, and that is very heavy. That is very heavy, both in terms of time and space, because when you want to scale it up, and this will become the bottleneck. We will also study in the future, especially the bottleneck in the vanilla transformer is the memory access, right? We will definitely discuss more on this. And to reduce the time and the space complexity, there are various efforts have been made in the last few years. There are two major things which has been done in the direction to reduce the complexity. Of course, there are much more much more ways to reduce the complexity. Two such ways are One is implementation of the sparse attention, and second thing is something called low rank implementation. For example, I was just talking about calculating of the attention score for a given token, right? In the 512 input tokens, if you want to calculate the value of one token, or if you want to calculate attention score of one token, we need to go for rest of the 511 keys and multiply it and do the rest of the things, right? In sparse attention, instead of taking 511, we will logically choose some tokens, some number of tokens, which is a subset of the rest of the tokens. In our case, which will be subset of 511 tokens, which will be way less than 511 tokens. So if you do that, the multiplication obviously will reduce, and number of flops, that means number of floating operations, will always be reduced, and so the time and the space complexity. That is what's called a sparse attention, which is an approximation of the vanilla attention, or which is an approximation of the exact attention, right? And second way is low rank implementation. We all know about singular value decomposition, that's called SVD. There also we take one bigger matrices and we split it into couple of matrices and we will process it. The same or a similar approach has been followed here as well. We will take the n cross n, that was the complexity of it, and we will divide it into two matrices, and then we will process accordingly. So, and there are multiple other ways as well, but these are the major efforts in reducing the complexity, right? And what are the ways we have discussed, low rank or the sparse, those are all the not exact attention implementation, those are just the approximate attention implementation. Okay, and GPUs. So in the GPUs, we already discussed about the various memory hierarchies and the HBM. Only one thing which we didn't discuss is the kernels. So kernels, you can think it as a function. A function which executes on the GPU, some calls a routine or a subroutine. These are all called as functions which are executing on the kernels, right? I'll give just bit more information on the kernels before we wrap up the video. For example, there is something called Kernel Fusion, which will be discussing the down the line. But this is one of the concepts which was implemented almost whether you take the library better transformer, or whether you take the library faster transformer, or there are so much of variations of transformer library which is coming in. One of the common features you see is called Kernel Fusion. Even PyTorch 2.0 has the major release because of the Kernel Fusion. So fuse means, you know, right? I think addition of one to another element, that's called a fusion. So kernels, we are fusing the methods, or we are fusing the operations. For example, let's say there is two metrics, and if you want to do a dot product, or if you want to do multiplication of those two, and if you want to take the softmax out of it, let's take this example. If you want to do it in a normal way, maybe you might need two kernels. One is to multiply those two matrices, and another method to calculate the softmax out of it. In this case, one kernel, obviously the data has to roam from GPU memory to L2 cache to one or few of the streaming multiprocessor, and we will be done with the result of two matrices, and the output of that again will be writing back to this, right? And output of the matrices will be going to the second function or second kernel, which will be calculating the softmax. For that, again this data has to, the output data has to move to from GPU memory to L2 cache to streaming processor. But if we combine these two methods into one method, what can be done is, only one time we need to move the GPU data from GPU memory to L2 cache to SM, and there itself the function can be combined together, and things can be done. And as we know, tensor cores is much faster, and this memory access from the GPU is much slower compared to the fastness of this. So that can be done very easily. And I just taken one example of the kernels and kernel fusion, but in reality I think the implementation is much in more detail. I just take an example of softmax and the matrix multiplication. So that's it regarding the hardware part of it and the basics of it. And the next part we'll be discussing about how FlashAttention is making use of all these things and making the algorithms better. So we'll see you on the next video. Thank you.